manufacture was rejected on these grounds. 31. 32. A Lockheed M21 with D-21 drone on top. A Lockheed M21 with a D-21 drone on display at Seattle's Museum of Flight. The high temperatures generated in flight required special design and operating techniques. Major sections of the skin of the inboard wings were corrugated, not smooth. Aerodynamicists initially opposed the concept, disparagingly referring to the aircraft as a Mach 3 variant of the 1920s era Ford Trimotor, which was known for its corrugated aluminum skin. 33. The heat would have caused a smooth skin to split or curl, whereas the corrugated skin could expand vertically and horizontally and had increased longitudinal strength. Fuselage panels were manufactured to fit only loosely with the aircraft on the ground. Proper alignment was achieved as the airframe heated up, with thermal expansion of several inches. 34. Because of this, and the lack of a fuel sealing system that could handle the airframe's expansion at extreme temperatures, the aircraft leaked JP-7 fuel on the ground prior to takeoff. 35. Annoying ground crews. 19. The outer windscreen of the cockpit was made of quartz and was fused ultrasonically to the titanium frame. 36. The temperature of the exterior of the windscreen reached 600 degrees Fahrenheit, 316 degrees Celsius. During a mission. 37. Cooling was carried out by cycling fuel behind the titanium surfaces in the chines. On landing, the canopy temperature was over 572 degrees Fahrenheit, 300 degrees Celsius. 33. Some SR-71s featured red stripes to prevent maintenance workers from damaging the thin, fragile skin located near the center of the fuselage. This portion of the skin was only supported by widely spaced structural ribs. 38. The Blackbird's tires, manufactured by B.F. Goodrich, contained aluminum and were filled with nitrogen. They cost $2,300 and would generally require replacing within 20 missions. The Blackbird landed at over 170 knots, 200 miles per hour, 310 kilometers per hour, and deployed a drag parachute to stop. The chute also acted to reduce stress in the tires. 39. Acquisition of titanium. Titanium was in short supply in the United States, so the Skunk Works team was forced to look elsewhere for the metal. Much of the needed material came from the Soviet Union. Colonel Rich Graham, SR-71 pilot, described the acquisition process. The airplane is 92% titanium inside and out. Back when they were building the airplane, the United States didn't have the ore supplies and ore called rutile ore. It's a very sandy soil and it's only found in very few parts of the world. The major supplier of the ore was the USSR. Working through third world countries and bogus operations, they were able to get the rutile ore shipped to the United States to build the SR-71. 40. Shape and threat avoidance. Water vapor is condensed by the low-pressure vortices generated by the chines outboard of each engine inlet. The second operational aircraft, 41, designed around a stealth aircraft shape and materials, after the Lockheed 12, 41. The SR-71 had several features designed to reduce its radar signature. The SR-71 had a radar cross-section, RCS, around 110 square feet, 10 square meters. 42. Drawing on early studies in radar stealth technology which indicated that a shape with flattened, tapering sides will reflect most energy away from a radar beam's place of origin. Engineers added chines and canted the vertical control surfaces inward. Special radar-absorbing materials were incorporated into sawtooth-shaped sections of the aircraft's skin. Cesium-based fuel additives were used to somewhat reduce exhaust plumes' visibility to radar, although exhaust streams remained quite apparent. Keller-Johnson later conceded that Soviet radar technology advanced faster than the stealth technology employed against it. 43. The SR-71 featured chines, a pair of sharp edges leading aft from either side of the nose along the fuselage. These were not a feature on the earlier 3 design. Frank Rogers, a doctor at the Scientific Engineering Institute, a CIA front organization, discovered that a cross-section of a sphere had a greatly reduced radar reflection, and adapted a cylindrical-shaped fuselage. By stretching out the sides of the fuselage. 44. After the advisory panel provisionally selected Convair's fish design over the A3 on the basis of RCS, Lockheed adopted chines for its A4 through A6 designs. 45. Aerodynamicists discovered that the chines generated powerful vortices and created additional lift, leading to unexpected aerodynamic performance improvements. 46. The angle of incidence of the delta wing scout be reduced for greater stability and less drag at high speeds, and more weight carried, such as fuel. Landing speeds were also reduced, as the chines vortices created turbulent flow over the wings at high angles of attack, making it harder to stall. The chines also acted like leading edge extensions, which increased the agility of fighters such as the F-5, F-16, F-18, MiG-29, and Su-27. The addition of chines also allowed the removal of the planned canard foreplanes. N5, 47, 48, air inlets. The air inlets allowed the SR-71 to cruise at over Mach 3.2, with the air slowing down to subsonic speed as it entered the engine. Mach 3.2 was the design point for the aircraft, its most efficient speed. 33. However, in practice the SR-71 was sometimes more efficient at even faster speeds depending on the outside air temperature as measured by pounds of fuel burned per nautical mile traveled. During one mission, SR-71 pilot Brian Shaw flew faster than usual to avoid multiple interception attempts. Afterward, it was discovered this had reduced fuel consumption. 49. Operation of the air inlets and flow through the propulsion system at the front of each inlet. A pointed, movable inlet cone called a spike was locked in its full forward position on the ground and during subsonic flight. When the aircraft accelerated past Mach 1.6, an internal jack screw moved its spike up to 26 in, 66 centimeters, inwards, 50. Directed by an analog air inlet computer that took into account pitot static system, pitch, roll, yaw, and angle of attack. Moving the spike tip drew the shock wave riding on it closer to the inlet cowling until it touched just slightly inside the cowling lip. This position reflected the spike shock wave repeatedly between the spike center body and the inlet inner cowl sides, and minimized airflow spillage, which is cause of spillage drag. The air slowed supersonically with the final plane shock wave at entry to the subsonic diffuser. 51. Downstream of this normal shock, the air is subsonic. It decelerates further in the divergent duct to give their desired speed at entry to the compressor. Capture of the plane's shock wave within the inlet is called starting the inlet. Bleed tubes and bypass doors were designed into the inlet and engine nacelles to handle some of this pressure and to position the final shock to allow the inlet to remain started. Air and flow visualization at unstart half-axis symmetric inlet at Mach 2. In the early years of operation, the analog computers would not always keep up with rapidly changing flight environmental inputs. If internal pressures became too great and the spike was incorrectly positioned, the shock wave would suddenly blow out the front of inlet, called an inlet unstart. During unstarts, afterburner extinctions were common. The remaining engine's asymmetrical thrust would cause the aircraft to yaw violently to one side. SAS autopilot and manual control inputs would fight the yawing. Often the extreme off angle would reduce airflow in the opposite engine and stimulate sympathetic stalls. This generated a rapid counter-yawing, often coupled with loud banging noises, and a rail ride during which crew's helmets would sometimes strike the cockpit canopies. 52. One response to a single unstart was unstarting both inlets to prevent yawing, then restarting them both. 53. After wind tunnel testing and computer modeling by NASA Dredon Test Center. 54. Lockheed installed an electronic control to detect unstart conditions and perform this reset action without pilot intervention. 55. During troubleshooting of the unstart issue, NASA also discovered that vortices from the nose chines were entering the engine and interfering with engine efficiency. NASA developed a computer to control the engine bypass doors which countered this issue and improved efficiency. Beginning in 1980, the analog inlet control system was replaced by a digital system, which reduced unstart instances. 56. Engines. The SR-71 was powered by two Pratt & Whitney J58, company designation JT11D20, axial flow turbojet engines. The J58 was a considerable innovation of the era, capable of producing a static thrust of 32,500 lbf, 145 kN. 57. 58. The engine was most efficient around Mach 3.2. 59. The Blackbird's typical cruising. A Pratt & Whitney J58, JT11D20, engine on open display at Evergreen Aviation Museum, a preserved AG330 start kart speed. At takeoff, the afterburner provided 26% of the thrust. This proportion increased progressively with speed until the afterburner provided all the thrust at about Mach 3.57. Air was initially compressed and heated by the inlet spike and subsequent converging duct between the center body and inlet cowl. The shock waves generated slowed the air to subsonic speeds relative to the engine. The air then entered the engine air compressor. Some of this compressor flow, 20% at cruise, was removed after the fourth compressor stage and went straight to the afterburner through 6 bypass tubes. Air passing through the turbojet was compressed further by the remaining 5 compressor stages, and then fuel was added in the combustion chamber. After passing through the turbine, the exhaust, together with the compressor bleed air, entered the afterburner. 60. At around Mach 3, the temperature rise from the intake compression, added to the engine compressor temperature rise, reduced the allowable fuel flow because the turbine temperature limit did not change. The rotating machinery produced less power but still enough to run at 100% RPM, thus keeping the airflow through the intake constant. The rotating machinery had become a drag item. 61, and the engine thrust at high speeds came from the afterburner temperature rise. 62. Maximum flight speed was limited by the temperature of the air entering the engine compressor, which was not certified for temperatures above 800 degrees Fahrenheit, 430 degrees Celsius. 63. Originally, the Blackbird's J58 engines were started with the assistance of 2 big Wildcat V8 internal combustion engines, externally mounted on a vehicle referred to as an AG330 start cart. The start cart was positioned underneath the J58, and the 2 big engines powered a single, vertical drive shaft connecting to the J58 engine and spinning it to above 3,200 RPM, at which point the turbojet could self-sustain. Once the first J58 engine was started, the cart was repositioned to start the aircraft's other J58 engine. Later start carts used Chevrolet big block V8 engines. Eventually, a quieter, pneumatic start system was developed for use at main operating bases. The V8 start carts remained at diversion landing sites not equipped with the pneumatic system. 64. 65. Fuel. KC-135 and SR-71 during an in-flight refueling. An SR-71 refueling from a KC-135Q Strato tanker during a flight in 1983. Several exotic fuels were investigated for the Blackbird. Development began on a coal slurry power plant, but Johnson determined that the coal particles damaged important engine components. 33. Research was conducted on a liquid hydrogen power plant, but the tanks for storing cryogenic hydrogen were not of a suitable size or shape. 33. In practice, the Blackbird would burn somewhat conventional JP7, which was difficult to ignite. Tossed at the engines, triethylborane, TEB, which ignites on contact with air, was injected to produce temperatures high enough to ignite FJP7. The TEB produced a characteristic green flame, which could often be seen during engine ignition. 49. On a typical mission, the SR-71 took off with only a partial fuel load to reduce stress on the brakes and tires during takeoff and also ensure it could successfully take off should one engine fail. 35. Within 20 seconds aircraft traveled 4,500 feet, 1,400 m, reached 240 miles per hour, 390 kilometers per hour, and lifted off. It reached 20,000 feet, 6,100 m, of altitude in less than 2 minutes, and the typical 80,000 feet, 24,000 m, cruising altitude in another 17 minutes, having used 1/3 of its fuel. 19. It is a common misconception that the planes refueled shortly after takeoff because the jet fuel leaked. The leaking of fuel was an intentional design feature because the high heat generated by the aircraft made it impossible to fully seal the fuselage tanks against leaks. 66. However, the amount of fuel that leaked was not enough to make the refueling necessary. The planes refueled because the maximum speeds of the aircraft were only possible with aerial refueling. 67. The SR-71 also required in-flight refueling to replenish fuel during long-duration missions. Supersonic flights generally lasted no more than 90 minutes before the pilot had to find a tanker. 68. Specialized KC-135Q tankers were required to refuel the SR-71. The KC-135Q had a modified high-speed boom, which would allow refueling of the Blackbird at nearly the tanker's maximum airspeed with minimum flutter. The tanker also had special fuel systems for moving JP4, for the KC-135Q itself, and JP7, for the SR-71, between different tanks. 69. As an aid to the pilot when refueling, the cockpit was fitted with a peripheral vision horizon display. This unusual instrument projected a barely visible artificial horizon line across the top of the entire instrument panel, which gave the pilot subliminal cues on aircraft attitude. 70. Astro-inertial navigation system. Nortronics, Northrop Corporation's Electronics Development Division, had developed an astro-inertial guidance system, ANS, which could correct inertial navigation system errors with celestial observations for the SM-62 Snook missile, and a separate system for the ill-fated AGM-48 Skybolt missile, the latter of which was adapted for the SR-71. 71. Before takeoff, a primary alignment brought the ANS's inertial components to a high degree of accuracy. In flight, the ANS, which sat behind the reconnaissance systems officers, RSOs, position, tracked stars through a circular quartz glass window on the upper fuselage. 49. Its blue light source star tracker, which could see stars during both day and night, would continuously track a variety of stars as the aircraft's changing position brought them into view. The system's digital computer ephemeris contained data on a list of stars used for celestial navigation. The list first included 56 stars and was later expanded to 61. 72. The ANS could supply altitude and position to flight controls and other systems, including the mission data recorder, automatic navigation to preset destination points, automatic pointing and control of cameras and sensors, and optical or SLR sighting of fixed points loaded into the ANS